that one question. So whatever the important things are there, that let me give you here. So first thing, so basically there are three types of water: gravitational water, hygroscopic water, and capillary water. So if I take soil as a two-phase system, that is soil, solids, and water. This complete thing is water. If all the voids are completely filled by water, then that capacity of the soil is nothing but called as saturation capacity. Now, some amount of the water will flow under the action of gravity. So that water is not available for the plants. This is your gravitational water. Which is not at all available for the plants. Then this is called field capacity. What is field capacity? It is the maximum amount of moisture content which is held in the soil against the force of gravity. So it is the maximum amount of moisture content which is held in the soil against the force of gravity. Now you get one more thing. Permanent wilting point. So it is the moisture content below which if water content drops, plants start wilting. Means if water content drops below PWP, plants start dying. So the water which is available for plants for extraction is this water. This is your capillary water which you call. Now remaining water is nothing but hygroscopic water. So remaining water, this water is nothing but your hygroscopic water. Now again, in this capillary water, complete capillary water is not easily available for the plants. So we take one more level, that is nothing but called as optimum moisture content. So this is your basic diagram here. So two things you are supposed to find out. First thing, which is the important point in this one, is storage capacity of soil. So this formula you have to remember: storage capacity of the soil, or you can also call it as available water or available moisture. So this is designated by y. I shall designate by y. Y is equal to S into D into Fc minus PWP. So storage capacity of the soil denoted by Y. S is specific gravity. Which is equal to gamma D by gamma W. D represents depth of root zone. Then Fc is your field capacity. PWP is permanent wilting point. So first equation that you are supposed to remember is this one. Hello? Yes, everything is working fine. So these are the points which you have to remember with respect to storage capacity of soil. First point. Second important point is readily available moisture depth. So represented by dW. So dW is about approximately about 75% of your storage capacity of soil, or dW is equal to S into D into FC minus OMC. So OMC is nothing but optimum moisture content. OMC is nothing but optimum moisture content. Okay. Third point which you have to remember is frequency of irrigation. So represented by small f. So frequency of irrigation small f is equal to dW divided by consumptive use. So CU represents consumptive use. So these are 3 points. Fourth important point is the relationship between base period, duty and delta. Very, very important. So relation between base period, duty and delta. So D is equal to 8.64 B by delta, where D represents duty. Units will be in hectare per cubic. B is base period. Delta is, this is delta. Base period should be in terms of days. Base period should, base period should be in terms of days. Delta should be in terms of meter. These are 4 important points. Next, fifth one, you have to remember some irrigation efficiencies. So first one is water conveyance efficiency. So I will represent it by neta C. So neta C, in short, you remember in a simple way, it is the ratio of water delivered to the water released in the canal. Water delivered to field divided by water released to canal into 100. So these efficiencies are important. Basically, I am giving you important points. Based on this only, you may get a question. So second thing is that water application efficiency. Neta A. So water application efficiency is given by nothing but water stored in the root zone divided by water stored in a root zone divided by water delivered to field into 100. So these two formulae are important. You may get a question based on this. Next, third efficiency is water use efficiency, not important. So next, water use efficiency is not important. Water storage efficiency is important. So water use efficiency eta u. So it is a ratio of water used beneficially, including water required for leaching to the water delivered into 100. So this formula is not so important. You can forget this one. Water use efficiency is not important. Fourth one is water storage efficiency. So it is a ratio of water stored in root zone divided by water required to bring moisture content to field capacity into 100. So this you have to remember, this is important. Okay. Then fifth one. So water distribution efficiency, not important. So eta d is equal to 1 minus yd by ym into 100. So yd represents average deviations from a mean. So what is the meaning of this? In a theoretical class, I solved a problem. Ym means mean depth of water stored. So fifth one, not so important. These are some irrigation efficiencies. Next, sixth point is some irrigation requirement of crops. So first one, consumptive irrigation requirement. In short, you can call it as CIR. This is equal to consumptive use minus effective rainfall. So CU is consumptive use. RE represents effective rainfall. So effective rainfall means the water which is useful for irrigation, which is obtained naturally due to rainfall. Second one, net irrigation requirement. In short, you can call it as NIR. This is equal to CIR plus leaching. Second one. Third one is field irrigation requirement. In short, FIR, which is equal to net irrigation requirement divided by application efficiency. Last fourth one is gross irrigation requirement. GIR is equal to field irrigation requirement divided by conveyance efficiency. So these are about irrigation requirements. So these you require. Then culturable command area. In short, you can call it as CCA. So CCA is equal to gross command area minus uncultivable area. Gross command area minus uncultivable area. So GCA is representing gross command area. Eighth one, intensity of irrigation. So intensity of irrigation means it is the percentage of CCA which is proposed to be irrigated annually. Percentage or percentage of cultivable command area proposed to be irrigated annually. So ninth point, capacity factor. So capacity factor CF is equal to mean discharge of a canal to the maximum discharge of canal. So generally this value will be less than 1. Mean discharge divided by maximum discharge, it will be less than 1. So ninth important point. 10th important point. It is time factor. So time factor TF. So time factor TF is equal to number of days The canal has actually run to the number of days, the canal was supposed to run. So this also will be generally less than 1. 11th point, discharge required in the canal Q is equal to area divided by duty. So you can write area divided by duty is nothing but 8.64 B by D. Sorry, B by delta. So these are very, very important. Last point, what is important is that design and discharge. Design and discharge QD is equal to Q divided by capacity factor into time factor. So design discharge QD is equal to discharge divided by capacity factor into time factor. So this is about your irrigation requirement, water requirement of crops. Now next thing, diversion network. So in this you have to remember the cross section of the diversion network. So assume that this is your ground level. So first thing on the upstream side, there will be a launching apron. So after launching apron, there will be a block protection. Then after block protection, there will be your impervious floor. So this is impervious floor. Okay. So after impervious floor, there will be inverted filter. Then after inverted filter, you will get again launching apron. So after that, again your ground surface continued. Now here you may get sheet piles or cut-off piles. So sheet piles. So this I will take it as D1. This I will take it as D2. So above there will be a weir here. So one by one, let me name it. You have to remember the dimensions. So first one is launching apron. This is first, second, third, fourth, fifth. So first one is launching apron. Second one is block protection. Third one is impervious floor. Fourth one is inverted filter. Fifth one is again launching apron. So cutoff walls D1 and D2 two cutoff walls I have taken here. First one launching apron width will be about 1 times D1 to 1.5 times D1. So next block protection will be, the width of block protection will be D1. So the width of your inverted filter will be 1 times D2 to 1.5 times D2. Even your launching apron in the downstream side will be 1 times D2 to 1.5 D2 generally. So these are some points which you are supposed to remember. This is your VL. Now there are three theories. In that three theories, try to remember all the three theories. Simple theories. First one is Blitzkrieg theory. First one is Blitzkrieg theory. So in a Blitzkrieg theory, suppose if you have considered this as your floor, so this is your ground surface. This is your hydraulic structure. Water. So depth of water, let me consider it as capital H. So three cutoff walls, let me take. D1, D2, D3. So the movement of water is assumed that water will percolate with respect to the impervious layer. So with respect to floor. So this is the assumed movement of water, which is practically not correct. Okay. Now here, total creep length will be, so H is nothing but head loss or head causing flow. L, that is your seepage length, or you can call it as creep length. Creep length L is equal to, suppose if I take this horizontal dimension as B, so if I take this horizontal dimension as B, Now total creep length L will be equal to 2 times D1 plus 2 times D2 plus 2 times D3 plus B. So your hydraulic gradient I will be equal to H divided by L. So H by L will be the hydraulic gradient. Now next thing, thickness of the floor required. So thickness of the floor required. 3 cases. First case, so this is your hydraulic gradient line. So assume that you have inserted a piezometer tube here. Okay. Now let me take the dimensions. So this is your thickness of the floor. So no water on the downstream side. So if you insert a piezometer tube, water level will rise till this level. This is your hydraulic gradient line. This thickness, let me take it as T, thickness of the floor. So remaining this height, let me take it as H. Okay. Now here, for such kind of diagram, so if you start deriving, T is a thickness, T is thickness of floor. H measured above top of a floor. If H is measured above the top of the floor, then in that case, what will be your equation? So equations for minimum thickness will be T minimum. So this case you can take it as no water on floor, no water on a downstream, and H measured from top of a floor. So for this criteria, your T minimum thickness of the floor required will be equal to H divided by Gc minus 1. Gc is the specific gravity of your concrete. H I have shown in the diagram. So design thickness T design will be 4 by 3, which is factor of safety. into H divided by Gc minus 1. So these are the equations. Suppose same thing let me take. Suppose if I take a case 2, same criteria, slightly change. So what I will do is that I'll take water on downstream side, water on downstream, and H measured from top of the floor. Suppose if I take in that way, so diagram I have to show you. So same diagram you will get, only one small change. Same diagram you will get. Only thing is that there is some water on the downstream side. So water depth, let me take it as Y. Y represents here depth of water on downstream. So in this case, if you start solving from T minimum you will get it as H minus Y divided by Gc minus 1. Design thickness T design, you will get it as 4/3 is the factor of safety into H minus Y divided by Gc minus 1. So these will be your equations. So next, lens weighted creep theory. So nothing but some weightage factors you are supposed to provide. So he proposed weightage factor for horizontal creep So weightage factor is 1/3. For vertical creep, weightage factor is 1. So whatever your Blix creep theory, whatever we have discussed here, whatever creep length will be there. So this creep length, in case of your lens weighted creep theory, same diagram, everything same. So here you will get B/3. So creep length L will be equal to 2d1 plus 2d2 plus 2d3 plus B/3. This is the only change. So horizontal width we have to divide by 3. That is the only change in lens weighted creep theory. Rest of the all story is the same as that of Blix creep theory. Next is Kosla's theory. So according to Kosla's theory, whatever the sheet pile we are going to provide, sheet pile is more useful on a downstream side. So horizontal width is B. Depth of cutoff wall is D. Now let me show some 3 points. So this point I'll consider it as C. This point I'll consider it as D. This point I'll consider it as E. Now, some equations you have to remember. First one, that is exit hydraulic gradient. Exit hydraulic gradient GE is equal to H divided by so exit hydraulic gradient GE is equal to H, that is nothing but head causing flow in the diagram you can see. So pi into D square root of lambda. So where D is the depth of cutoff wall, lambda is equal to 1 plus square root of 1 plus alpha square divided by 2. Then alpha is equal to B by D. Everything is being defined in the diagram. So this formula you have to remember. Now next thing is that something called piping. So piping is nothing but backward erosion of soil. Now here, if exit hydraulic gradient is greater than a critical hydraulic gradient, then piping occurs. If exit hydraulic gradient is greater than critical hydraulic gradient, then piping occurs. So factor of safety for piping is given by IC by I exit. So, or IC by G exit. GE you can write. So I exit you write in case of your geotechnical engineering. Now IC for critical hydraulic gradients, there are some formula. I hope so you remember. Specific gravity of soil minus 1 divided by 1 plus E. E is void ratio. So GS is specific gravity of soil. E is void ratio. Now there are some equations for uplift pressure heads. So uplift pressure heads equations, not so important. So uplift pressure at C will be equal to 0. Uplift pressure at point D will be equal to H divided by pi cos inverse of lambda minus 1 divided by lambda into pi by 180. Pressure at E is equal to h by pi cos inverse of lambda minus 2 divided by lambda into pi by 180. So these are the formulas that you are supposed to remember. Actually, it is not so important. Your wish. Am I clear with this thing here? Next. So some equations with respect to canals. So in canals, first thing is that Kennedy's theory, not so important. So first equation is for critical velocity. Critical velocity V0 is equal to 0.55 d to the power 0.64. So where V0 is critical velocity, in meter per second, d is depth of flow. Second one, velocity of flow to avoid silting and scouring. So it will be Vk is equal to 0.55 m d to the power 0.64. So where this is your Vk in meter per second, m is critical velocity ratio. Now, next theory is very, very important. You may get a question based on this. Lacy's regime theory. So here there are some equations that you have to remember. So first equation is for silt factor. Silt factor F is equal to 1.76 square root of D, where D is mean soil particle size in mm. Second equation, velocity formula. So velocity V is equal to Q into F square divided by 144 to the power 1 by 6. So this Lacy's theory is very important. You may get a question based on this. Question that too, it will be very easy. Directly formula I can ask, formula based question directly. Either you'll ask formula or some values you'll give, you have to calculate. So third one, perimeter. So perimeter P is equal to 4.75 square root of Q. So P is in a meter, Q should be in terms of meter cube per second. Here velocity in a meter per second, Q in terms of meter cube per second. So these are three important formula. In that second one and third one, very important. Fourth formula. So fourth formula is for longitudinal slope. So longitudinal slope S is equal to F to the power 5 by 3 divided by 3340 Q to the power 1 by 6. Then one more velocity formula is there. Velocity V is equal to square root of 2 by 5 F into R. Not so important. Sixth one, Lacey's scour depth. (1.35) into Q square divided by F whole to the power 1 by 3. Small q is equal to Q divided by B. That is discharge per meter width. Discharge per meter width. So meter cube per second per meter will be the units here. So these are some equations which are very important with respect to Lacey's regime theory. So components functions of diversion network separately, a separate video I have recorded. I hope so you can go through that one. Okay, we shall take a small break and then we shall continue. So break for 15 minutes, we shall continue. So if you know R value, then you can find out velocity using this formula. F and R is known, then you can use the fifth formula for finding out the velocity. Still there are n number of formulae. All formulas I'm not giving. This is more than sufficient. Still there are n number of formulae here. Not required that much. Okay, we shall take a small break of 15 minutes and then we shall continue. Hello. Hello.
Hello, sir.
Yeah, tell me.
Good morning, sir.
Good morning.
Sir, I was asking when will class start? So like there's like blank screen, so that's why.
Irrigation, very small thing. Now, small things are left out. I'll complete.
Okay, sir. Thank you.
Okay, thank you. So next, last important topic is gravity dams for you. So from gravity dams, you will not get a design part or something. So based on some formula, you will get directly a question. Okay. So last it was in 2016, you got a question from gravity dams. Before that, it was in 2008. So it is not so important, but still you may get a problematic question. Some points I will give, try to remember. First thing is that modes of failure of gravity dam. In that, one of the mode is overturning. So for overturning, your factor of safety equation will be resisting moment divided by overturning moment. Resisting moment divided by overturning moment. Second one, sliding. So here, there are two things. So factor of safety for sliding, first one. So F is equal to mu into summation of vertical forces divided by summation of horizontal forces. So mu is a coefficient of friction. So its value will be between 0.6 to 0.75, not required. Why? Because it is only required for ESE people. So you remember only the formula. Summation of V is algebraic sum of vertical forces. Summation of pH is algebraic sum of horizontal forces. Now there is a factor called sliding factor. Tan theta is equal to summation of pH divided by summation of V. If possible, remember, or else not required. According to me, from exam point of view, this formula is only important. Next formula which is important is shear friction factor. It is important. So shear friction factor, in short, SFF, I will write. It is equal to mu into summation of V plus B into 1 into Q. Most of the people don't write that 1. The other dimension it is. So generally I write it summation of P into H. So B is width of joint or section. Q represents shear strength. So this formula is again important. So you may get a problematic question, direct all the values will be given, just substitute and get the answer. So this is important. Next thing is you may get a problem based on uplift pressure. So to find out uplift pressure, So 3 diagrams I'll give you totally. So based on that, any one thing can be asked. So first thing, so this is the first criteria. So without downstream water, only upstream water. No water on downstream. So this is the first case. No water on downstream and no drainage gallery. In this case, your uplift pressure diagram will be purely a triangle. So at this point, it will be 0. At this left hand side, it will be gamma W into H. So this is your uplift pressure diagram for first case, that is no water on downstream side. So second case, so to find the total uplift force will be equal to area of pressure distribution diagram. So you have to find the area of the pressure distribution diagram, this thing. So this will give you the total uplift force. Second case, is that with downstream water. So downstream water, let me take it as H. In this case, you will get a trapezoidal pressure distribution diagram. This will be the pressure distribution diagram in second case. So here in this case, so here it will be gamma W into H. Here it will be gamma W into small h. So to find out the total uplift force, you have to find out the area of pressure distribution diagram. So the same thing. So total uplift force will be equal to area of pressure distribution diagram. This is the second case. Third case, is that with a drainage gallery. With a drainage gallery. Now here in this case, your uplift pressure distribution diagram, so will be slightly modified. So such kind of uplift pressure distribution diagram you will get here. So this will be gamma W into H. This will be gamma W into small h. And this ordinate it will be gamma W into small h plus 1/3 of capital H minus small h. So you have to find out these values, then you have to draw the diagram. So finally, area of a pressure distribution diagram. Will give you total uplift force. Your 2016 question was based on this diagram itself. Next thing, wave force. So wave force, there are two equations. So there are a few equations. In that one equation, two is very important. So first one is your height of the wave. HW is equal to, again there are two equations here for height of the wave. So one equation I'll give, that is more than sufficient for you. 0.032 square root of V into F. So here HW will be in terms of meter. V is wind velocity in kilometer per hour. F is fetch in a kilometer. So this equation is applicable when F is greater than 32 kilometer. So when F is less than 32 kilometer, there is one more equation. It is little bit lengthy, not required. Second one, not so important equation. Pressure intensity due to waves. PW is equal to 2.4 gamma W into HW. So this is pressure intensity due to waves. So total pressure PW will be equal to 2 times gamma W into HW square. So these points you remember, these are more than sufficient with respect to wave pressure, wave force. Next one is with respect to silt pressure. P silt is equal to, total silt force is equal to, so half into gamma submerged into H square, that is the depth of your silt, into Ka. So Ka is your coefficient of active earth pressure. I hope so you remember. 1 minus sine phi divided by 1 plus sine phi. So this is your silt pressure. Not so important. You can leave this silt pressure. Sixth point, some formula in elementary profile of a gravity dam. So first point, minimum base width required. So minimum base width required, first one. So minimum base width of dam In that, two criteria are there. First one, for no tension condition, B is equal to H divided by square root of S minus C. So H is the height of depth of water on the upstream. S is nothing but your specific gravity. C is uplift pressure coefficient. Second one, for no sliding condition, B is equal to H divided by mu S minus C. So two equations. Third equation, limiting height of dam. HC. Here you remember, C is uplift pressure coefficient. Uplift pressure coefficient. If no uplift, C will be equal to 0. Full uplift, you are supposed to take C is equal to 1. So full uplift condition given in the question means you have to take C is equal to 1. If he has given no uplift condition, then C will be equal to 0. So limiting height of dam HC is equal to EFC is divided by gamma W into S minus C plus 1. So same things, everything is the same. So FC is nothing but permissible compressive stress in concrete. Gamma W is unit weight of water. S is specific gravity of the material. C is uplift pressure coefficient. If a full uplift, you have to take it as 1. If no uplift given, C should be equal to 0. That criteria you have to remember. Next thing, stresses in dam. Stresses on foundation soil. So two equations are there. So first point what you have to remember is that in this, in case of reservoir full condition, Pmax will be at toe, P minimum will be at heel. Suppose if it is a reservoir empty condition, in case of reservoir empty condition, Pmax will be at a heel, P minimum will be at toe. So equations, Pmax is equal to summation of vertical forces divided by base width B, 1 plus 6E divided by B. So where E is eccentricity, minimum will be, P minimum will be equal to summation of vertical forces divided by base width B, 1 minus 6 times eccentricity divided by base width B. Now, two more points you have to remember. Theoretical points, it can be asked in the examination. Maximum permissible eccentricity is B by 6. To avoid tension at the base of dam, the resultant should fall within the middle third of the base. Middle third of the base width. So this is important point. It is called a middle third rule. Nothing but suppose if this is your base width. So this is your dam. So if this complete width is B, so if this complete width is B, suppose if I divide into 3 parts, B by 3, B by 3, B by 3. Suppose if I take this is the center part, that is B by 2, B by 2, then eccentricity should be within these two things. So middle third of the rule, this is B by 6, B by 6. Within this middle B third, your resultant should fall. That is the meaning of that ninth point. So am I clear with these things? So these are the equations and all which you require from this subject, that is irrigation engineering. So these are more than sufficient. If you remember all this, try to remember all this. Within this, you can get one question. And some theoretical points I have told which are important. So those you remember. For example, what is a siphon aqueduct? What is an aqueduct? Okay, those points you remember. Those are more than sufficient. So you remember what is aqueduct, what is a siphon aqueduct, some more these points. Aqueduct. Generally, it should not be asked because last year asked. So these 4 points you remember, that is more than sufficient. So these are more than sufficient, which are required for your exam point of view. So anything else you want to ask, you can ask. It may be from hydrology or irrigation. So we shall discuss. So today for you, class will be Geotech revision class. From 5 p.m. to 7:30 p.m. So actually it was supposed to be arranged in the morning itself. So sir is busy with some other class. So after irrigation immediately it was there, but sir is busy with another class. So it will be in the evening from 5 p.m. to 7 p.m. today. So am I clear with all these things? So these are more than sufficient for your examination. Try to study, especially first chapter is most important. Most of the times you get question from this initial things only. So from the storage capacity or duty formula based on duty. So based on this only you will get generally a question. Anything you want me to ask? If you want to ask, you can ask, or else we shall end the session. And today remember evening 5 to 7:30 p.m. it will be geotechnical engineering revision class. Okay, I hope so there are no doubts. So let me end this session. So all the best for your exam. Okay. So after the class, immediately I'll be uploading the notes. So remaining chapters from irrigation are not so important. If you want, you can revise them, otherwise not required. So most of the times question come from these parts itself. So all the best.